Welcome everyone to our session. I was already introduced, but my name is Marcelo Altman. I work as a senior software engineer at Readyset. Prior to Readyset, I was working as a senior software engineer at Percona, where I led the Percona Extra Backup project, an online tool backup for MySQL. I'm a long-time MySQL community contributor. I have spoken in various events, often write blog posts, and also am organizing a few events here and there. I'm a member of the Oracle ACE, which is something I'm really proud of. I have been contributing with fixes to MySQL code, so I'm also a MySQL code contributor, including the last MySQL 9.3 release, where we, from Readyset, we provided a patch in order to provide like micro third decimal places for milliseconds on MySQL client. So right now you can see the full picture. Before it was only two decimal places. Readyset is written in Rust. Like, we rely very heavily on the Postgres and MySQL drivers. So I'm also a contributor on the Rust MySQL driver.
I'm Gautam. I'm the CEO of Readyset. My past has been, I was at DataRobot, Azure for a very long time in Microsoft. I was in a startup called as StoreSimple, and then a bunch of other sort of tech companies, primarily focused on distributed systems, file systems, storage systems, caching systems. So that's sort of really my background.
Cool. Let's start talking about database scaling. Why we need to scale a database. In the end of the day, like, the database is running on a hardware that has a limited amount of resources. And when we start to run out of the resources, it's when we have to scale our database. Database normally doesn't really show up as part of our stack. It's in the end of our stack. But what really matters is the application performance. But database is the primary factor of application performance. So we need to ensure our database is performing in order for our application to be performing. In this talk, we will be talking about a caching solution. And one point I want to make is that a cache will never replace a database. Your database has to do a variety of things, including serving result sets, and a caching is a piece of this functionality which will speed up that part of the database. And by the end of this talk, our goal will be that any one of you here that either requires a high throughput on your application or require a low latency will be considering giving Readyset or a caching solution a shot. For this talk, we will be looking into how MySQL is performing a particular query and how Readyset will compare with that. We will be using the MySQL employees database. This particular query here, what we are doing is we are counting the number of active employees we have in each department. So it's a query that has an aggregation, it has a join, and it has a predicate. By just downloading the employees database without doing any optimization, MySQL runs this particular query in around 437, half a second. So the first thing, in order to scale this particular query, we'll have to look into the execution plan. So the execution plan of this query is telling us that we are doing a table scan on the department employees database. For each row, it will have to execute a filter in memory, which is our predicate on toDate to only count active employees. For each row it gets, it will do an index, primary key lookup on the department. It will aggregate this particular data into a temporary table. And once it has done looping through all the records, it will then scan this temporary table in order to give the results back. So the first thing we can see here is that we are doing a table scan which is not optimized. So we can create an index for this particular query. Creating an index on the department employees database using the predicate and the join clause makes the execution plan change. Right now, this query is executing first, going into the departments table, getting the 9 rows from there, and then right now, instead of a full table scan, it's doing an index, covering index lookup, which is super optimized. The rest of the execution plan continues the same. We still have to aggregate the data and scan this particular table. But we can see that our execution time, our latency has dropped from 500 milliseconds to 152. So by just adding an index, we were able to scale this query like 3 times. The next thing is MySQL provides you some capability of caching, which is the InnoDB buffer pool. So we also want to ensure that our buffer pool is sized correctly in order to be serving pages from memory and not having to go into disk for every single query that we do. MySQL exports a status that we can check if a particular query is going into the disk or not, which is the InnoDB buffer pool reads will tell the amount of pages it had to fetch from this, while read requests, it's the pages that have been read into memory. By sizing buffer pool enough to fit this particular query in memory, we can see that also like the latency has dropped another 20, 30 milliseconds. Right now we are being able to execute this query in 138 milliseconds. If we have a look of what is going under the hood when MySQL is executing this query, we can have a look into this flame graph, which will print all the functions that MySQL it's doing when it's executing this query. The flame graph shows us, basically, we can split these in 2. We have the part on the left, which is the first point I want to make, which is like your database has to do a lot of other things. Here, we are spending half of the execution doing like row search MVCC, which means that we have to be looking into each particular page, if we have like older versions of this page, into the undo logs in order to serve a consistent view of this page. And also these here, we are reading raw pages. Even those pages are already in memory, we still have to do like all the work in order to traverse all the B-tree in order to get these rows. And the second thing is on the right side here of this graph, we are spending time on the temp table handlers. 1, doing an index read, and 2, doing updates, which means that for every time we execute this query, we are doing the calculation and the aggregation over and over again. So if we execute this query 10 times, we have to recalculate the whole aggregation every single time. So let's have a look how much can a particular server execute this query before we run out of resources and we have to scale this hardware, like having have to create a new read replica or something like that. So we can execute perf_stat in order to check how much CPU time has been executed or used to execute this query. And we can see that this query took 136 milliseconds to execute. So this test was done in a machine that has 16 cores. So we can get the potential queries per second that this machine can execute before running out of resource by dividing the amount of cores by the time it takes to execute the query, which is 16 cores machines divided by 136 milliseconds, give us a potential queries per second of 117 queries per second of this particular query on this hardware before we have to either put more CPUs or add new read replicas. So Readyset. Readyset is a result of a PhD thesis on the MIT, which is called Partial State in Data Flow Based Materialized Views. In the database community, it's also known as NORIA. Readyset is source available. Like you can go to our GitHub, download, compile Readyset, or even provide patches to us. We have two softwares. It's Core, which is like the binary that we produce, and we also have like a cloud offering, which is where we manage Readyset for you. In a nutshell, Readyset implements like two important things. The first one is we implement the wire protocol of Postgres and MySQL. Different from other caching solutions that you have to implement a specific API on your application, Readyset it's compatible with the wire protocol of MySQL. So the same way you do a query in MySQL, you will be doing a query in Readyset, and it will be able to figure out if that's a cache or if it is something it has to proxy to the database it is connected to. And the second thing is that Readyset implements a data flow underneath it, which again, different from other caching solutions that are out there. There is no TTL or invalidation. We subscribe to MySQL, we read MySQL binary logs, and as the data changes on your database, because with this data flow graph we can trace back which keys are involved in a particular cache, we are able to keep the cache always up to date. So if you have put something in cache on Readyset, that cache will always be refreshed as the data changes. So there is no TTL, there is no invalidation. Your cache view, it's always fresh as your data changes. I have done a talk in Belgium during FOSDEM last year, which explains exactly how this data flow graph works underneath. So if you want to check out, here it's the link to the video. But we are going to look the exact same query. Again, since we implemented wire protocol, this looks exactly the same. The only difference there is that we are now connected to Readyset, and Readyset executes this query in sub-milliseconds. Having a look on the potential queries per second for Readyset executing this query, we can see that the CPU time taken to execute this query, it's 65 microseconds. So executing exactly the same metric as before, if we get the 16 cores divided by the amount of time it took, we now get 24,000 queries per second in comparison to 117, which is a 209x improvement in query latency and query per second. But we are talking about scaling down your database. Like we want to save costs. So a machine with 16 cores on AWS on this CPU family will cost 61 cents per hour. We can get Readyset running on a machine that it's 2 CPUs that cost only 7 cents per hour. Readyset will still be able to deliver 3,000 queries per second on that machine, which is a way lower spec. It will still give you 26x improvements in queries per second. Looking into the price, a MySQL running on the 16 cores will cost you roughly like $5,000 per year, while Readyset on the 2 CPU machines will cost only $670. This gives you an 8 times cheaper costs, while still delivering 26x improvements in queries per second, and each single execution of this query will still be 209 improvement in latency. Now it's time for us to do a quick demo. Hopefully it works. So here we have the exact same query running on MySQL. I have a background process that is hiring and firing employees. So we can see the data, it's changing. Right now, the query is executing in MySQL. It's taking around 110 milliseconds to execute, which is giving us roughly 10, 11 queries per second. I will click now, and this query destination will change to Readyset, and we will be able to see the performance improvement. So right now we are executing this on Readyset. It's taking about 30 microseconds to execute. We can see that the data is still flowing. So the write process is still writing, and we are fetching always a live data of this particular query. One thing while I was developing this thing that was not matching is that the queries per second here are not correct if we look the latency this particular query it's giving. So while troubleshooting what was going on, I figured out that we here are taking more time to display the data on screen than actually querying Readyset. So implementing a refresh rate, if we increase the amount of times we decrease the amount of time that we print data on the screen, we can actually get like the true queries per second with this latency, which is around 25,000 queries. Cool. That was the demo. It worked. Awesome. Back to Galton.
All right, that was an awesome demo. And so we're going to talk a little bit at a slightly higher level about the big ideas around Readyset. There are two big ideas that I'd like to sort of plant in your mind. One question that might come up in everybody's mind is, hey, what if we just had a database that is completely in memory? You would get similar kind of performance. I mean, it's a completely in-memory database. And so does Readyset seem like a practical solution? And to that end, I would sort of show you a graph on the right-hand side. In practice, as many of you have probably seen, in practice, you will find that queries that hit your backend database generally follow Zipfian distribution. What that means is, imagine that you have, say, 20 queries that are being generated by your application. You will generally find that the top 3 or 4 queries occur at a far higher frequency than all of the other queries put together. So as a result, what happens is the top 3 or 4 queries generally generate about 60–70% of the load on your backend database. So with a very small cache, with a very limited amount of memory, if you're able to just cache the first 3 or 4 queries, you will get a massive improvement in resource utilization in your backend database. So that's sort of really the crux or the reason for why just taking care of these small details really matters. As you saw the entire flame graph from the previous slides, what you would see is inside the flame graph, there is a lot of time and CPU that is being spent by a general purpose database doing stuff that is not of much consequence. If the data is not changing, if indexes are not to be sort of referred to or whatever, you generally end up still going down all of those code paths in a regular general purpose database, but which is of absolutely no consequence in a real system. And so that is the real crux of what Readyset is sort of focusing on. We have sort of turned the database around by saying that, hey, we are just going to cache the specific queries that we really care about, and the only time there is any kind of a CPU cycle inside the system is when there are updates that are happening in the backend database. When there are updates that are happening, they flow to us through the replication stream. We evaluate the changes that are happening to update the actual query results, and that takes a very, very small amount of CPU, which is why Readyset as a caching solution is a very, very simple, cheap alternative to boosting your performance in your system. And of course, I mean, the big thing out here that you should also take away is that less work is better, less work is faster. And Readyset does a very minimal amount of work in order to deliver what you need. Less work means better scalability, as you have already seen, like 250 times improvement you get essentially on this kind of a thing. What this also means is the amount of infra that you need is far lesser. So it's not just the one query, you have thousands of queries, and if you start caching your queries, you will get humongous amounts of reduction in your infrastructure spend. And so obviously less infra means less cost, less management overheads, fewer people to manage a lot of these systems, and it starts becoming an easier problem for people to solve. Leaving that aside, we're going to start taking a look a little bit into the future of what Readyset is building out, and this is sort of an invitation to everyone to sort of participate in this entire thing that we're building. I just want to talk a little bit about like how current operational data systems are architected. You will generally have like an application that sits right on top, and the application talks to a load balancer or some sort of an application logic that starts distributing queries to your primary database or your read replica. So this is a very, very typical kind of a system. This kind of system works perfectly fine. You have an application team that's constantly churning out new features. Maybe once in a week, once in 2 weeks, there's a brand new drop which comes up with new queries. These new queries now need to be accommodated inside your system. So you would generally say, hey, do I have enough room inside my primary and my read replicas to accommodate these new queries that have been generated? If not, add new replicas, and that's sort of the way that a lot of teams sort of scale out their systems. So this is a very, very traditional system. What is happening and what is changing now are the kind of applications that people are developing are all sort of AI LLM based applications. What are the implications of this? A couple of implications are speed development. I mean, we've all heard of the whole vibe coding, movement that's going on right now. People are generating applications at a much faster pace than you can possibly think of. Within, what used to take months is now taking days, probably hours to sort of generate. The other aspect of this kind of a speed of development is also that there are very unpredictable patterns that are coming out in the queries that are being generated by these applications. Many of the queries are likely being generated through text to SQL kind of conversions. Many of the queries are being generated out of applications that are just, they come up ad hoc for a certain amount of time and then they go back down. And the question that I have for many of you, and this is a question that I'm sort of trying to figure out myself, is like, how would you be able to manage a database infrastructure capable of managing these kinds of applications that are being churned out on a day-to-day basis? How does your database infrastructure scale out? How does it actually perform when with this kind of a rapid pace and rapid growth in applications? So that's sort of just one point that I wanted to sort of highlight. And so this is sort of our understanding or our belief in what we think is a good architecture to sort of take this entire thing forward. And so what we are saying is where you had essentially a query router that sat in the middle, or a load balancer that sat in the middle, and which indiscriminately sent your queries to your backend databases. It's indiscriminately sent your queries to your read replicas or your primary. We now need a far more intelligent kind of a system that sits in the middle that starts absorbing these queries. And the second aspect is, because the query patterns are changing on a day-to-day basis, this intelligent query router needs to understand how these queries are actually changing, what are the changes in these patterns, and adapt the system automatically to absorb some of these things. So sort of the mnemonic that I've sort of, the icon that I've chosen out here is something that absorbs like these protuberances that are coming from your application. That's the thing that we think is the right way to do it. Readyset, of course, has got a fantastic solution to absorb these kinds of crazy protuberances. I mean, we have tons of customers who are using it for the Black Friday event or the Cyber Monday event, because again, the queries spike up like crazy. You don't have to go crazy, adding lots and lots of hardware during those events, but that exact same architecture also lends itself really well to absorbing these kinds of interesting kind of query patterns that are coming up because of these kinds of LLM applications. So that's sort of the way that we think about like how the entire architecture should be evolving. We see that there is a room for this kind of a intelligent query router that sends that detects the changes in queries, that monitors the queries that are going through the system, and automatically starts caching the queries that are causing the most amount of pain to your backend database. And again, like I said, I mean, this thing needs to be dynamic. It needs to be real time. So this is not something you can just do once a week and sort of let it go, because there's a lot of changes that are happening out here. So this is really like the name of our new feature, or rather initiative. It's called as Readyset Query Pilot. We have sort of been working on it for a couple of months now, and we continue to work on it, and we would certainly invite folks to come out and sort of give us some really good input on this front. But we think of Query Pilot as being dependent upon three basic things. Number one, we need a industrial grade, really solid proxying capability, which, thanks to Proxy SQL, we are able to sort of, get excellent features from that. We need intelligent decision-making query monitoring capabilities, which allows us to dynamically reflect upon the queries that are happening and then make decisions. And then finally, we need a rock-solid caching system, which is able to actually cache these kinds of queries. And obviously, the future is fairly open. Apart from caching, there are other optimizations that might be possible with the queries that are happening to the system. But this is like a really good, solid foundation for how we can build systems that are resilient to the changing dynamics in the application development space that we are going through. Just a quick word about Proxy SQL. We've been using Proxy SQL the last 4 or 5 months. We are totally in love with it. We use it fundamentally really to build this entire infrastructure that we just spoke about Query Pilot. We have a ton of customers who are using Proxy SQL, but just a quick sort of this thing about how we are using it internally inside Readyset. For folks who are interested to understand how Readyset could help you to sort of optimize your systems, like I said, the way that Readyset works is we pick and choose the queries that are most impactful to your backend database, and we can start caching those kind of queries. Reach out to us for a free consultation, free assessment, and we'd be happy to help you through this entire thing. That's about it from our end. We do have some freebies, some Readyset hats. If folks are interested, please feel free to come by and pick it up. Thank you.